Welcome to the 5th class on complex analysis. Today we discuss the Cauchy product of two complex power series. Let sigma an z minus a the whole raised to n and sigma bn z minus a the whole raised to n be two complex power series. Here an and bn are two complex sequences. We define an infinite matrix whose rows and columns are indexed by the sequences an and bn. The first column of this matrix are a0, b0, a0, b1, a0, b2 and so on. The elements of the second column are a1, b0, a1, b1, a1, b2 and so on. Here a0, b0 is called the first diagonal entry of this matrix. a0, b1, a1, b0, these elements are the second diagonal entries of this matrix. Similarly, the third diagonal entries are a0, b2, a1, b1, a2, b0 and so on. In general, the nth diagonal entries are a0, bn, a1, bn minus 1, etc. an, b0. We now define a new sequence Cn whose nth term is defined as Cn is equal to a0 bn plus a1 bn minus 1 plus etc. an b0, and this is the sum of the nth diagonal entries of this infinite matrix, and this summation can be written as summation k is equal to 0 to n ak bn minus k, or equivalently summation ai bj, I plus j is always n. This new sequence is called the Cauchy product of the sequences an and bn. We now define a new power series sigma n is equal to 0 to infinity Cn z minus a the whole raised to n. That is the power series C0 plus C1 into z minus a plus C2 into z minus a the whole square plus etc. Here C0 is the element a0, b0, that is the first diagonal entry of the matrix, and C1 is a0, b1 plus a1, b0, and this is the sum of the second diagonal entries and so on. And this new power series is called the Cauchy product of the power series sigma an z minus a the whole raised to n and sigma n is equal to 0 to infinity bn z minus a the whole raised to n. Similarly, we can define the sum of two power series, that is, given two power series sigma n is equal to 0 to infinity an z minus a the whole raised to n and sigma n is equal to 0 to infinity bn z minus a the whole raised to n. The sum of these two power series is defined as the power series sigma n is equal to 0 to infinity an plus bn into z minus a the whole raised to n. That is the series a0 b0 plus a1 b1 into z minus a plus a2 b2 into z minus a the whole square plus etc. And this series is called the sum of these two power series. Next, consider the power series sigma n is equal to 0 to infinity an z to the power n and sigma n is equal to 0 to infinity bn z to the power n both the power series is equal to n is equal to 0 to infinity z to the power n. That is the geometric power series. Obviously, the radius of convergence of each power series is 1. Here the coefficients of sigma z to the power n are 1, 1, 1, etc. So the limit supremum is 1. So the radius of convergence of sigma an z to the power n and sigma bn z to the power n are both equal to 1. Now the question is, what is the radius of convergence of the Cauchy product of these two power series? And note that the coefficient of z to the power n in the Cauchy product is given by Cn is equal to a0 bn plus a1 bn minus 1 plus etc. an b0. Here all coefficients are 1. So this is the sum of n plus 1 terms, that is 1 plus etc. n plus 1 times. Therefore Cn is equal to n plus 1. So the Cauchy product of the power series sigma z to the power n and sigma z to the power n is the power series sigma n is equal to 0 to infinity n plus 1 z to the power n. And note that here the coefficient of z to the power n is n plus 1. But the radius of convergence of the power series is given by r is equal to limit of an divided by an plus 1, that is limit of n plus 1 divided by n plus 2, and the limit of this sequence is 1. So in this case, the radius of convergence of the first power series, that is an z to the power n is 1, that is denoted by Ra. Ra is the radius of convergence of the first power series, and Rb the radius of convergence of the second power series, that is also 1, and Rab the radius of convergence of the Cauchy product, that is equal to 1. So in this case, Ra radius of convergence of the first power series is equal to the radius of convergence of the second power series is equal to the radius of convergence of the Cauchy product of these two power series. Now consider another example. Let sigma n is equal to 0 to infinity an z to the power n is equal to 1 plus 2 into summation n is equal to 1 to infinity z to the power n. That is the first power series. And the second power series n is equal to 0 to infinity bn z to the power n is equal to 1 plus 2 into summation n is equal to 0 to infinity minus m the whole raised to n z to the power n. So the Cauchy product of the series sigma n and sigma bn is given by sigma Cn z to the power n, where Cn is a0 bn plus a1 bn minus 1 plus etc. an b naught. We can easily verify that Cn is equal to 0 for all n. Therefore the Cauchy product of these two power series is equal to 0 plus 0 into z plus 0 into z square plus etc. And note that the radius of convergence of the first power series, that is 1 plus 2 into summation n is equal to 1 to infinity z to the power n. So the coefficients are 1, 2, 2 etc. So in this case the radius of convergence is 1. Similarly, the radius of convergence of the second power series is also 1, and the radius of convergence of the Cauchy product is infinity. Here all the coefficients are 0. That is 1 by r is equal to limit superior of mod a n raised to 1 by n. Here 1 by r is 0. Therefore r is equal to infinity. Here the radius of convergence of the Cauchy product is greater than Ra and Rb. Now I move on to the theorem, and this theorem states that if sigma an z minus a the whole raised to n and sigma bn z minus a the whole raised to n be two power series with a radius of convergence greater than or equal to r. That is, if r is the radius of convergence of this power series and rb is the radius of convergence of this power series, then ra and rb are greater than or equal to r. And let sigma n is equal to 0 to infinity Cn z minus a the whole raised to n be the Cauchy product of the power series sigma an z minus a the whole raised to n and sigma bn z minus a the whole raised to n, then the radius of convergence of the Cauchy product of these two power series is also greater than or equal to r. Similarly, the radius of convergence of the sum of the power series, that is summation n is equal to 0 to infinity an plus bn z minus a the whole raised to n, and this is the sum of these two power series, and the radius of convergence of the sum of these two power series is also greater than or equal to r. And on the disk with the center a and radius r, the sum of the power series, that is summation n is equal to 0 to infinity an plus bn z minus a the whole raised to n. This series converges to the sum summation n is equal to 0 to infinity an z minus a the whole raised to n plus summation n is equal to 0 to infinity bn into z minus a the whole raised to n. Moreover, the product series sigma n is equal to 0 to infinity Cn z minus a the whole raised to n converges to this sum for all z in the open disk with the center a and the radius r. Let us go to the proof of this theorem. So assume that Ra be the radius of convergence of the power series sigma an z minus a the whole raised to n, and Rb is the radius of convergence of the power series bn z minus a the whole raised to n, and Ra plus b be the radius of convergence of the sum of these two power series, that is sigma an plus bn z minus a the whole raised to n, and Rab is the radius of convergence of the Cauchy product of the given power series. Then it is given that the radius of convergence of the first power series and the radius of convergence of the second power series, that is Ra and Rb, are greater than or equal to r. That is given in the statement of the theorem. Ra and Rb are greater than or equal to r. We want to show that the radius of convergence of the sum of the power series, that is Ra plus b, is also greater than or equal to R, and the radius of convergence of the Cauchy product of the given series is also greater than or equal to R. First, we show that the radius of convergence of the power series sigma an plus bn z minus a the whole raised to n is greater than or equal to R. To prove this, consider an arbitrary element in the open disk with a center A and radius R. And we will show that this open disk is contained in the open disk with the center A and radius R A plus B. So let Z be an arbitrary point in this open disk. And note that the real number R is less than both RA and RB. And here RA is the radius of convergence of the first power series. So the first power series sigma an z minus a the whole raised to n is convergent for every z such that mod z minus a is less than RA. Since R is less than or equal to RA, the power series sigma an z minus a the whole raised to n is absolutely convergent. Since the radius of convergence of the power series is RA and small r is less than or equal to RA, the power series sigma an z minus a the whole raised to n is absolutely convergent. That means this series is a convergent series. Similarly, since R is less than or equal to RB, here RB is the radius of convergence of the second power series sigma bn z minus a the whole raised to n. That series is also absolutely convergent. That means this sum is also finite. Now consider the sequence of partial sums of the series sigma mod an into z minus a the whole raised to n. That is, for m is equal to 1, 2, 3, etc. we get the sequence of partial sums of the series sigma mod an into z minus a the whole raised to n. And observe that this sequence of partial sums is a monotonic increasing sequence, and that sequence is bounded above by this term. Similarly, the sequence of partial sums of the series sigma bn into z minus a the whole raised to n is monotonic increasing and bounded above by this term. Now consider Sm is the m plus 1 the partial sum of the series sigma an plus bn into z minus a the whole raised to n. That is, when m is equal to 1, 2, 3, etc., we get the sequence of partial sums of the series sigma an plus bn into z minus a the whole raised to n. Obviously, this sequence of partial sums is a monotonic increasing sequence, and we will show that this sequence is also bounded. Now the partial sum Sm can be written as summation n is equal to 0 to m mod an into z minus a the whole raised to n plus bn into z minus a the whole raised to n. By triangle inequality, this can be written as summation n is equal to 0 to m mod z minus a the whole raised to n plus summation n is equal to 0 to m, not n, summation n is equal to 0 to m modulus of bn into z minus a the whole raised to n. But this sequence of partial sums is bounded above by this term, So this is less than or equal to MA, and the second sequence of partial sums is also bounded above by MB. So the sequence of partial sums of the series is bounded above by MA plus MB, and this sequence of partial sums is monotonic increasing and bounded above. Therefore the sequence Sn is a monotonic increasing sequence and bounded above by this. So the sequence Sn is a convergent sequence, and this sequence is convergent means the series sigma an plus bn z minus a the whole raised to n is absolutely convergent. Hence the series sigma an plus bn into z minus a the whole raised to n is absolutely convergent and hence convergent. So if we take any arbitrary element in the open disk with the center A and radius r, then the power series sigma an plus bn into z minus a the whole raised to n is absolutely convergent. But note that Ra plus b is the radius of convergence of this power series, and this power series converges for all z such that mod z minus a is less than r, and this means that the open ball with the center A and radius r is contained in the open ball with the center A and radius Ra plus b. This means that R is less than or equal to Ra plus b. Next, we claim that for every z in the open disk with the center A and radius r, the power series sigma an plus bn into z minus a the whole raised to n converges to this sum. For that, consider an arbitrary element z in the open disk. And note that for every z in this open disk, the power series sigma an into z minus a the whole raised to n converges. Here note that Ra is the radius of convergence of the power series sigma an z minus a the whole raised to n, and small r is less than or equal to Ra. Therefore the power series is convergent for every z within the disk BAR. That means the series is convergent means the sequence of partial sums converges to this sum. Similarly, the sequence of partial sums of the second series, that is the series sigma bn into z minus a the whole raised to n, also converges to this sum. Now consider this difference, and this is the m plus 1 the partial sum of the series sigma an plus bn into z minus a the whole raised to n. Now consider this difference. By triangle inequality, this can be written as summation n is equal to 0 to m an into mod z minus a the whole raised to n minus summation n is equal to 0 to infinity an into z minus a the whole raised to n plus summation n is equal to 0 to infinity bn into z minus a the whole raised to n minus summation n is equal to 0 to infinity bn into z minus a the whole raised to n. And since the series sigma an into z minus a the whole raised to n is convergent, the sequence of partial sums converges to this sum. That is, when m tends to infinity, this sequence of partial sums converges to this. That means the modulus of this term tends to 0 as m tends to infinity. Similarly, the modulus of this term also tends to 0 as m tends to infinity. And this means that this sequence of partial sum converges to this limit. That means that the series sigma an plus bn into z minus a the whole raised to n converges to the sum sigma an into z minus a the whole raised to n plus sigma bn into z minus a the whole raised to n. Next, we will prove that the radius of convergence of the product series is greater than or equal to r. So, to prove this, take an arbitrary element in the open disk with the center A and radius r, and take an arbitrary element m in n, and we will prove that the product series, that is the Cauchy product series sigma n is equal to 0 to infinity Cn z minus a the whole raised to n is absolutely convergent for every z in the open disk with the center A and the radius r. So now consider the sequence of partial sums of the series sigma n is equal to 0 to infinity mod Cn into z minus a the whole raised to n. So Sm n is equal to 0 to m mod Cn into z minus a the whole raised to n, m is equal to 0, 1, 2, 3, etc. And these are the sequence of partial sums of the series sigma mod Cn into z minus a the whole raised to n. And we will show that this sequence is a convergent sequence. Now Sm can be written as summation is equal to 0 to m mod Cn into z minus a the whole raised to n, and this is summation n is equal to 0 to m. By definition, Cn is the Cauchy product of the sequences an and bn. So Cn is defined by summation k is equal to 0 to n ak into bn minus k into z minus a the whole raised to n. So by triangle inequality, this can be written as summation n is equal to 0 to m, summation k is equal to 0 to n modulus of ak into modulus of bn minus k into modulus of z minus a the whole raised to n. And this term, that is mod z minus a the whole raised to n, can be written as modulus of z minus a the whole power k, and this term can be written as mod z minus a the whole raised to k into mod z minus a the whole raised to n minus k. So the sequence of partial sums Sm is less than or equal to summation n is equal to 0 to m, summation k is equal to 0 to n modulus of ak into mod z minus a the whole raised to k into mod bnk into mod z minus a the whole raised to n minus k. This is equation number 1. Now we define an is equal to, that is capital An is equal to an into z minus a the whole raised to n, and capital Bn is equal to bn into z minus a the whole raised to n, and Cn is the Cauchy product of these two sequences. Here n is equal to 1, 2, 3, etc. And since mod z minus a is less than r, the series sigma n is equal to 0 to infinity an, that is sigma n is equal to 0 to infinity an into z minus a the whole raised to n is absolutely convergent. Similarly, the series n is equal to 0 to infinity capital Bn is also absolutely convergent for all z in the open disk with the center A and radius r. And observe that these two series are absolutely convergent. So by Cauchy multiplication theorem, the product series, that is summation n is equal to 0 to infinity Cn, that is the series. Here Cn is the Cauchy product of the sequence An and Bn. So the Cauchy product is also absolutely convergent. That means the series summation n is equal to 0 to infinity mod Cn is convergent. Now summation n is equal to 0 to infinity mod Cn is equal to summation n is equal to 0 to infinity, and Cn is modulus of summation n is equal to 0 to infinity mod ak into mod bn minus k, and this series is convergent series. This series is convergent means the sequence of partial sums is convergent, and this means that for each positive integer m, the sequence of partial sums is bounded by this term. That is, for each m, modulus of, can note that in this summation modulus of ak into bn minus, this is always positive. Each term is always positive. Therefore, this modulus is not necessary. That is, for each m in n, modulus of summation n is equal to 0 to m, k is equal to 0 to m mod ak into mod b n minus k is less than or equal to m, and this is finite. That means the m plus 1 the partial sum of the product series, that is modulus of summation n is equal to 0 to m, summation k is equal to 0 to n, and mod ak into mod bn minus k is this term. This is less than m. Then look at equation number 1. Look, equation number 1 is Sm, that is the m plus 1 the partial sum is equal to this, but we have proved that this is less than or equal to m for all m. That is, the sequence of partial sums Sn is bounded by m. That means that is the sequence of partial sums is bounded by m for all m. Thus the sequence Sm is an increasing sequence and bounded above. That means the sequence Sm is a convergent sequence. That means the series summation n is equal to 0 to infinity Cn into z minus a the whole raised to n is absolutely convergent and hence convergent. And this means that the open ball with the center A and radius r is contained in the open ball with the center A and radius RAB. That means R is less than or equal to RAB. Next we show that this series converges to this sum. And note that the series sigma an z minus a the whole raised to n and sigma bn z minus a the whole raised to n are absolutely convergent on this open disk. So by Cauchy multiplication theorem, the product series converges to the sum sigma an into z minus a the whole raised to n into sigma bn z minus a the whole raised to m for all z in the open disk, the center A and radius r. So this completes the proof of the theorem.